Hi chemistry friends, it is section 4 of chapter 15 where we are looking at equilibrium constants to calculate the concentration or pressure of a reactant or product at equilibrium. But more specifically, suppose that we were given the Kc or the Kp and initial concentrations, but we're not given equilibrium concentrations. So we're going to look at several examples in this kind of situation where we will use ice tables. We'll summarize the initial conditions, look at the changes that occur, and then using equilibrium values that include a variable, we will plug it into the expression to solve for x, and then take x, figure out what those equilibrium values are. That will allow us to find those equilibrium concentration values. Problems thus far have asked us what is the K equilibrium constant, knowing different circumstances. Here, these kinds of problems say the equilibrium constant is 55.64 for this reaction. It has been determined at this temperature. If we know that 0.13 moles each of both reactants is placed in a 25-liter flask. So we're going to need to find our concentration by taking our moles divided by 25 liters. The question is asking us, though, what are the concentrations of H2, I2, and HI when the system reaches equilibrium? Here's our strategy we're going to use. We're going to write our equilibrium constant expression, and we're going to make an ice table. We're going to put in our initial concentrations that were given for both of our reactants. We're going to assign the variable x to represent our changes in concentration. We're going to look at our stoichiometric coefficients. We have 1, 1, and 2. So we're going to lose reactants, so losing x for both H2 and I2. We're going to gain product, and because there's 2 there, we're going to gain 2x. Then we will take and enter the expressions for our final equilibrium concentrations with the x variable in there and set it equal to our K value given. We're going to solve for x. Then we can take that x value that we're solving for and plug it into our ice table into the equilibrium values that had the x in it, so we can get those final concentrations of each species. First, we've got our K expression. We had H2 plus I2 making 2 HI. So we've got our product squared over H2 times I2, and that equals 55.64. Now we're going to make our ice table. All right, we were told that our initial concentration, the H2 and I2 both had 0.130 moles in a 25-liter container. So I'm going to do 0.13 divided by 25 to get my molarity. And I got 5.2 times 10 to the negative 3 for both of my reactants. Remember, at time 0, I have no products formed. We said our change in concentration, those are both 1, so we're going to lose x, and we're going to gain product, gain 2x. So I'm going to write the equilibrium expression here. I'm going to have 5.2 times 10 to the negative 3 minus x. And I'm going to write the same for my iodine, 5.2 times 10 to the negative 3 minus x. And for my equilibrium here, 0 plus 2x. I'll just leave it as 2x. Now we're going to plug in these values into our K expression. All right, does yours match mine? My Kc is equal to 55.64, and that's equal to my concentration of HI, we've got 2x squared, divided by 5.2 times 10 to the negative 3 minus x, and 5.2 times 10 to the negative 3 minus x. We could also write this as 5.2 times 10 to the negative 3 minus x squared, right? Because this times the same number is squared. Okay, now we got to start reducing because we need to solve for x. The first thing I notice is that I've got a squared on the numerator, a squared on the denominator, so I could get rid of both of those squares as long as I square root the left side of my equal sign. So let's do that first. That left me the square root of 55.64 with 7.459. Now we need to cross multiply. So I need to do 7.459 times that by 5.2 times 10 to the negative 3 minus x. So I'm going to need to distribute and multiply that times each other and 7.459 times x. All right, here I simplified it even more. I showed that I did the 7.459 times 5.2 times 10 to the negative 3 gave me this. And then I distributed that, so I got minus 7.459x is equal to 2x. Now let's add 7.459x to both sides. And then to get x by itself, I need to divide what it is attached to. So divide both sides by 9.459. That should give us x is equal to 4.101 times 10 to the negative 3. We're not done yet. That's just what x equals. We need to take this number and put it back into our ice table in the equilibrium line. So if I look back here to find my concentration at equilibrium, I need to do 2 times that x value to get my concentration of HI. I need to take 5.2 times 10 to the negative 3 and minus that x value to get my concentrations for hydrogen and for iodine. So let's do that. The concentrations for hydrogen and for iodine, I plugged in my 5.2 times 10 to the negative 3 minus my x value, and I rounded to 3 significant figures, so 1.10 times 10 to the negative 3 molarity, moles per liter. And for HI, we had to do 2 times x. So 2 times the value I just found with 3 sig figs, 8.20 times 10 to the negative 3 m. Using the same reaction, let's look at this example. At some temperature, Kc is 33 for that reaction. Assume the initial concentrations for both the hydrogen and iodine are 6 times 10 to the negative 3 moles per liter. Find the concentration of each reactant and product at equilibrium. Using the same strategy we just did, see if you can set this up. Let's see where you're at. I plugged in for my initial concentration the 6.00 times 10 to the negative 3 for hydrogen and for iodine. Again, remember, initially I have no product. I lose reactants, I gain products, and I'm gaining double the products. So my equilibrium values would be 6.00 times 10 to the negative 3 minus x for both reactants. And for products, it would be 0 plus 2x, or we can just say 2x. Our K equilibrium expression, products, so HI squared over both reactants is equal to 33. I was given that. So now we just need to solve for x. When I plugged my values in, yes, I would have 6.00 times 10 to the negative 3 minus x times 6.00 times 10 to the negative 3 minus x. When I have both of the same multiplying each other, I simplified it and I just squared it. Then I can look at this and go, oh, if I have a squared and I get rid of those squares, I can square root the left side, leaving me with 5.744 is equal to 2x over 6.00 times 10 to the negative 3 minus x. Now let's cross multiply. After I distribute my 5.44 times 6 times to the negative 3 and my 5.44 times negative x, I get this. I'm going to add 5.744x to both sides and then divide both sides by 7.744. And I got an x value of 0.00445. But we're not done. We now need to take that x value and plug it into these equilibrium values to get my equilibrium concentrations. And when I did that, I got 0.0015 molar for both of my reactants and 0.0089 molar for my product. Double check the math. Let's look at our third and final example using the same equation. You're given 1 mole each of H2 and I2 in a 1 liter flask. What are the equilibrium concentrations of all species if we're given our equilibrium constant at 55.3? See if you can set up our ice table and figure that out. Let's see how you did. I set up my ice table. I was told 1 mole divided by 1 liter gives me concentration of 1 capital M molarity. And that's for both. And initially I have no product formed. So I'm going to subtract, I lose reactants, I gain products, and I gain 2x because I have a 2 in front of my product. So at equilibrium I have 1 minus x, 1 minus x, and plus 2x. Knowing my Kc is my products, HI squared, over both of my reactants times each other, I'm going to plug in my values. So 2x squared, 1 over x times 1 over x is equal to my K expression of 55.3. Because 1 over x times 1 over x is 1 over x squared, and then I have 2x squared on top, I'm going to simplify that and get rid of my squares and then square root my 55.3. Once I do that, I can solve for x. X is 0.788. And then I'm going to plug x into my equilibrium expression. So 1 minus 0.788 would give me a concentration of 0.21 for both my reactants. And when I do 2 times 0.788, 2x, I get a concentration of my product of 1.58 m. Now, while those last couple of examples are definitely harder than the ones that we've done before this, we might even have some trickier aspects coming. Suppose that you're studying the decomposition of PCl5 to form PCl3 and Cl2. Here's our expression, all 1-to-1 ratios. We know Kc. If our initial concentration of PCl5 is this, so we know our initial concentration, and we know that initially we have no products. What will the concentrations of reactants and products be when the system reaches equilibrium? First thing I'm doing is setting up my ice table. I was only given my initial concentration for my reactant. Again, I know that I have 0 products formed initially, but I'm going to lose reactant and I'm going to gain product, all 1-to-1 ratio. So at equilibrium, I'm going to have 0.0920 minus x, and x. Let's set up our K expression. K is equal to the concentration of PCl3 times the concentration of Cl2 all over my concentration of PCl5, and that's equal to 1.2. All right, I plugged in my equilibrium values. So products, x times x, over my reactants, 0.0920 minus x. Let's cross multiply. That gives me 1.2 times 0.0920 minus x, so I'm going to distribute that. X times x is x squared. That gives me 0.1104 minus 1.2x is equal to x squared. Is this starting to look like the quadratic equation? Let's get everything on one side and set one side equal to 0. So I'm going to add 1.2x to both sides, and I'm going to subtract 0.1104. Now I have my A value would be 1, my B value is 1.2, and my C value is negative 0.1104. And we can plug it into our quadratic formula. On our Canvas page, I posted a YouTube video for putting the quadratic formula into your, let's say your TI-83 or your TI-85 or whatever calculator that you have. Is the easiest way to do it and the quickest way to do it. I highly recommend having a quadratic formula program on your calculator. You can definitely plug it into the quadratic formula and do it the long ways, but highly recommend using your calculator. My calculator spits out 2 x values. It can be 0.08586 or it said negative 1.286. Now how do we tell which one it is? Let's look back here at my PCl5, and at equilibrium 0.0920 minus x. I can't have a negative value here, right? Because I'm going to lose some of my reactant. That means at equilibrium it's going to be a little bit smaller than 0.09. So that means I can't minus a negative. That would be adding and having a greater equilibrium concentration. So this won't work. But the minusing 0.08 does make sense. So now we can just take this x value and plug it into there, there, and there. So we can say that at equilibrium, the concentration of PCl5 is 0.0859. That would give us 3 significant figures. And that would be the same for chlorine's concentration and for PCl3. That would be my concentration there. And here I'm going to do 0.0920 minus 0.08586 to get a concentration of 0.00614 moles per liter. Although a solution to a quadratic equation can always be determined using the quadratic formula, In many instances, an acceptable answer can be obtained by using a realistic approximation to simplify the calculation. Let's look at another equilibrium. Let's say I have I2 in equilibrium with 2I. If I write my Kc, I'm told that my Kc, my equilibrium constant, is 5.6 times 10 to the negative 12. Holy smokes, this is a very small equilibrium constant. 10 to the negative 12. Let's set up our ice table, assuming that my initial concentration is 0.45 molar. Let's see what we have. All we're given here is our initial concentration of I2. Remember, initially, I don't have any products. There's no stoichiometric coefficient here, so I'm going to minus x. Here I have a 2, so I'm going to add 2x. So at equilibrium, I have 0.45 minus x. Here I just have 2x. Let's plug in our values into our K expression. So I have 5.6 times 10 to the negative 12 is equal to my products, 2x squared, divided by my reactants, 0.45 minus x. Let's do the math to cross multiply and simplify this equation. Now when I get here, we're going to get to the quadratic equation again, right? Because on top I'm going to have 2x squared, so that'll be 4x squared. I'm going to have a number value here, and I'm going to have an x value here. Can I solve it using the quadratic formula? Absolutely, but there is a simpler way to reach an answer. We see how very, very small Kc is, indicating that the change to I2 concentration is going to be very small. In fact, it's so small that subtracting x from the original concentration, 0.45, leaves it essentially unchanged. So that 0.45 minus x is pretty much going to be equal to 0.45. So we can drop the x in the denominator and have a simpler equation to solve. Think if that isn't there, then I can just multiply these two together and have an easier solution. Let's do it. When I cross multiplied, I did 0.45 times 5.6 times 10 to the negative 12. And I got 2.52 times 10 to the negative 12 is equal to 2x squared is equal to 4x squared. Divide both sides by 4, gave me 6.3 times 10 to the negative 13 is equal to x squared. Take the square root of both sides, and I got x was equal to 7.937 times 10 to the negative 7th. Let's look back at our original equilibrium concentration expressions. When I did 0.45 minus x, notice I got 0.449999. Again, that is so little of an amount that we lost, and that was being able to neglect x. If I did 2 times x, I got 1.587 times 10 to the negative 6 molarity. When is it acceptable to do this? Well, it turns out that if I were to take the K value given and times it by 100, if it's less than that original concentration, then we can avoid doing the quadratic equation, and it's not required. That's when we can drop that minus x in the denominator. Let's go back and look at the one that we just did. So up here, if I take my K value, which here is 5.6 times 10 to the negative 12, and I times that by 100, I actually get 5.6 times 10 to the negative 10. Is this value less than my original concentration? My original concentration was 0.45. This is way less than 0.45. 5.6 times 10 to the negative 10 would be point, and then having 9 zeros, and then 5/6. So yes, it is much smaller, meaning when I set up that K expression, I can drop this x because that amount is going to be so small. It's practically negligible. And that allows us to say, well, since that concentration of that original minus x, it's pretty much going to be equal to that original concentration because we lose so little of it. See if you can set this problem up. We have this chemical reaction. It contributes to air pollution whenever a fuel is burned in air at a high temperature, as in gasoline engines. At 1500 Kelvin, we're given our Kc is 1 times 10 to the negative 5th. Suppose a sample of air has a nitrogen concentration of 0.08 moles per liter and an oxygen concentration of 0.02 moles per liter before any reaction occurs. Calculate the equilibrium concentrations. First thing, we've got our ice table. We've got our N2 plus our O2. Those are our reactants. Here's our products. We were told initial concentrations for nitrogen and oxygen. Again, we always have 0 products at first. We lose reactants and we gain products, and I gain twice as many products because I have a 2 to 1 to 1 ratio. So my equilibrium, I'm going to have 0.08 minus x, 0.02 minus x, and 0 plus 2x. Plugging that into my equilibrium constant expression, we were told our equilibrium constant is 1 times 10 to the negative 5. So we have our products over our reactants, and I'm going to set it up like this. Now I could solve it like this. I could use the quadratic equation. Or I could say, hey, what is 100 times 1 times 10 to the negative 5th? That would be 1 times 10 to the negative 3. And that is smaller than either of my initial reactant concentrations. So I can drop the x in both of those. If you don't feel comfortable or you don't understand the rule, that's fine. You can solve it using the quadratic equation, and that's completely fine. Or you can simplify it. And like I said, we can drop the x so we can then have an easier equation. And then we would multiply, cross multiply. So whatever our 0.08 times our 0.02 times that by 1 times 10 to the negative 5th. That would give us 1.6 times 10 to the negative 8, which is equal to 2x to the second power would be 4x squared. Divide both sides by 4 and take the square root of it to give us x is 6.32 times 10 to the negative 5th. Then I'm going to take that x and I'm going to plug it in to each one of those equilibrium expressions, giving me 0.08 minus x, so a concentration of about 0.08. If I actually did this out, it's going to be 0.07999, about 0.08. It barely changes it. For oxygen, 0.02 minus that teeny little number, again, is about 0.02. It's barely touching it. And NO, I'm going to do 2 times x, and that would be 1.3 times 10 to the negative 4th m. This is our last example for the section. We have the decomposition of PCl5 to form PCl3 and Cl2. See if you can write the equation, balance the equation, and given our equilibrium constant and our initial concentration of PCl5, see if you can set up the ice table, the equilibrium expression, see if you can solve for x, and see if you can tell me those equilibrium concentrations. Let's see how you did. PCl5 decomposing into PCl3 and Cl2. Everything's balanced. It's all a 1 to 1 ratio. I'm told my initial concentration of my reactant, I have 0 products. So I'm going to lose reactant, gain product, giving me 0.1 minus x, x and x. If you really want a plus x there, that's fine. Setting up our expression, there we have it. Now you might be going, hey, do I have to use the quadratic equation here? Well, let's see. What is 100 times k? 100 times our k is 33.3. So 33.3 times 100 would be 3,330, and it is substantially greater than our initial concentration. So unfortunately, we have to use our quadratic equation. We can only do that if 100 times k is less than our original initial concentration. So we will distribute 33.3 times 0.1 and then 33.3 times negative x, leaving me with this reaction. And we want everything on one side to set it equal to 0. So I'm going to subtract 3.33 from both sides, and I'm going to add 33.3x to both sides, leaving me with x squared plus 33.3x minus 3.33. So my A value is 1, my B value is 33.3, and my C value is negative 3.33. When I plug that into the quadratic formula, I would get x is equal to 0.09970 or a negative value, but we know we can't use the negative value. That's not even possible. We would have negative concentrations. So then I'm going to plug in that 0.0977 into that x value and that x value. So that's both of the concentrations of my products. And then I'm going to do 0.1 minus that X value to get the concentration of my PCl5. And that wraps up this section.